Welcome to the Explainer. So today we're unpacking the truly incredible journey of neural networks. But, to really grasp how today's AI actually works, we can't just start with code or silicon. We've got to start with the only working model of true intelligence that we actually have, and that is biology. Let's dive right in. 86 billion. That's roughly the number of neurons inside your brain right at this very moment. Now, the big question is, how do 86 billion of these tiny individual cells actually come together to create intelligence, memory, and thought? Well, the secret is all in how they connect. And understanding that connection, that's the ultimate master key to understanding AI. Okay, part one, inside your brain. Let's physically map out this biological foundation before we even look at a single line of code. It's actually super intuitive when you break it down into plain English. You don't need a medical degree here. Just think of a neuron kind of like a tiny person. The dendrites, those are the ears of the cell, branching fibers just listening to thousands of signals from their neighbors. Then you have the cell body, or soma. That's the brain, actively tallying up all those incoming signals. And finally, the axon is the mouth, this long cable that transmits the final result outward. Ears, brain, mouth. It really is that beautifully simple. But the really crucial point is right between that brain and mouth. It's this tiny zone called the axon hillock. This is the neuron's literal decision point. The cell checks all the signals it just heard and asks basically one binary question. Is the total signal above my threshold? If it is, boom, the neuron fires. If it isn't, it stays entirely silent. That simple choice, to fire or stay silent, is the biological equivalent of an activation function. It's literally the fundamental unit of all intelligence. Moving on to part two, how neurons actually talk. So these physical cells actually have to communicate across a tiny, microscopic gap called the synapse. And I want you to imagine this dynamic sequence happening inside your head thousands of times a second. First, tiny packages called vesicles rush to the edge of the cell and just burst open. Second, these chemical messengers, neurotransmitters, float right across that empty synaptic gap. Third, they lock into matching receptors on the next neuron's ears. And finally, step 4, the signal successfully passes on. Now, here's the profound why behind this whole biological process. Why does this actually matter? Because the strength of that synapse can change. When you practice something, say playing piano or riding a bike, repeating this process literally grows more receptors. The physical connection actually gets stronger. The neurons wire together. This is physically what learning is. Keep that tucked in the back of your mind because this is exactly, and I mean literally exactly, what updating weights means in AI. All right, part 3, translating biology into math. Let's make the jump from biology to tech and translate these wet biological parts directly into math. It's wild how perfectly this maps out. Every single concept in a neural network is a direct copy of a biological part. Those dendrite ears, they become our mathematical inputs, which we call X. That crucial synapse strength we just talked about, that becomes our weight, or W. The cell body summing things up is literally just mathematical addition. The axon hillock's decision to fire becomes our activation function. And the axon, that's our output. It's biology on the left and pure math on the right. There is, I should mention, one extra mathematical trick we use in code that isn't strictly defined in biology. It's called the bias. You can kind of think of the bias as the artificial neuron's default mood. It's just a small extra number we add in that shifts how easy or hard it is for the neuron to fire, completely independent of whatever the inputs are doing. Let's see this in action. Part 4, the live artificial demo. I don't want to just talk about the math. I want you to actually see it. Here's our core formula in action. Z equals the inputs multiplied by their weights plus our bias. Watch how these numbers update. The artificial neuron is taking data in, multiplying it by the importance of that specific connection, and then adding its default mood to reach a final decision. Now, watch closely what happens as we drag these weight sliders down into negative numbers. Let's say negative 0.5. See that? The formula updates instantly, the total drops, and the neuron gets heavily suppressed. It essentially silences the signal altogether. We're actively deciding which ears to listen to and which to just ignore. And if we go up here to the drop-down menu and switch our activation function over to the original step function, just look at the output. It snaps purely to a strict binary, exactly 0 or exactly 1. It either fires or it stays completely silent. There is absolutely no in-between. This brings us to part 5, the 1943 breakthrough. Seeing that pure 0 or 1 actually brings up a super fascinating historical question. Where did this specific mathematical model actually start? Well, the year was 1943. Neurologist Warren McCulloch and a brilliant young mathematician named Walter Pitts published this radically titled paper, and guys, this was a massive paradigm shift. It was the very first mathematical model of a neuron, proving that the human brain could literally be treated as a logical computing machine. Now, to make the math work back in 43, they brutally stripped the biological neuron down to just 3 simple rules. 1. Inputs had to be strictly binary, 0 or 1. 2. Weights were totally fixed at 1, meaning all inputs were equal and there was absolutely no way for the network to learn. And 3. The thresholds were hand set by the designer. But remarkably, even with just those 3 rigid rules, they proved you could compute any logical operation.
All right, part 6, scaling up to today.
We all know that neural networks absolutely rule today's tech landscape, right? But getting from that 1943 paper to today was anything but a smooth ride, which kind of leads us to a bit of a mystery. If the 1943 math was so revolutionary and those early models were showing so much promise, why did the entire field of neural networks suddenly just die in 1969? Well, the culprit was actually a simple logic puzzle. A very influential researcher named Marvin Minsky proved mathematically that the early single-layer models couldn't even solve a basic logic problem called exclusive OR, or XOR. Because of that single limitation, the hype just completely collapsed. It sparked this painful AI winter. Funding completely dried up, and researchers basically abandoned neural networks for nearly 2 decades. But let's look at the timeline and see how this builds, because it really is a story of redemption. We start with that 1943 McCulloch-Pitts model. Then, the 1957 perceptron added the ability to actually learn by adjusting those weights. Then, bam, we hit the brick wall of the 1969 AI winter. But the true hero of our story arrives in 1986 with an algorithm called backpropagation. This finally allowed errors to flow backward through multiple, deep layers of neurons, updating millions of weights all at once. It literally broke the winter. And that brings us to today, where progress has gone into absolute hyperdrive. Modern neural networks are no longer just a handful of math equations on a chalkboard. We are stacking hundreds of millions of these artificial neurons in deep, complex layers. By combining that backpropagation breakthrough with massive modern datasets and insanely powerful GPUs, these networks learn exactly like the biological synapse does, by seeing millions of examples and tweaking those weights until they achieve intelligence. It's truly an incredible story, isn't it? We've taken the biological ears, brain, and mouth of a single cell, translated it into math, survived a decades-long AI winter, and reproduced an 80-year-old idea at a planetary scale. Which leaves us with one incredibly fascinating question to ponder as we wrap up this explainer. If we've achieved all of this with a radically simplified mathematical copy, what on earth is going to happen when we fully unlock the remaining secrets of those 86 billion biological cells inside your head? Thanks so much for joining me on this journey. Keep learning, and I'll see you on the next explainer.